Hello everyone, welcome back to the Quick Machine tutorial series. In this video we are going to be creating a transient solution inside of Quick Machine. So if you're familiar with the previous videos, up until now everything that Quick Machine has been able to do has been constrained to static solutions. So just as a quick reminder, once you've set your geometry, you've set your windings, if you come down to this finite element tab and click analyze, it'll pop up an FEMM window and it will create a mesh for your motor and actually solve the finite element analysis to create a static solution. So in this video we're going to look at how to create a series of static solutions in order to run a transient solution. So the two main things that we need in order to run a transient solution are your flux linkage curves and your torque curves. So in order to create your flux linkage curves, you need to run a static solution for every single one of these angles and every single one of these current values. So if you go down to the transient solution tabs, first thing it's going to ask you to do is to generate this data that we need to do for our transient solution. Basically generate these plots. So we need to tell it what values of current do we start, end, and increment. So here we're going to start at 1 amp and we're going to sweep by incrementing 1 amp at a time up to 100 amps. Now we need to tell it the rotor positions. And so in order to choose your rotor positions, you really just need to pick a phase. It doesn't matter what phase you want to pick. We can try phase C, for instance. So for phase C, we want to sweep our rotor from fully unaligned to fully aligned. So our fully aligned position is at 60 degrees and our fully unaligned position is, so there's 8 rotor lobes, that's 45 degrees between here and here, so that's 60 minus 22.5 is 37.5 degrees. So we're going to start at 37.5 and sweep down to 60. And this is obviously your increment value, so just click 1 again. And now you need to tell it what phase you're actually sweeping over. So here we want to sweep over phase C. Now, depending upon how many angles you have to actually compute, the number of static solutions can grow very, very large. For instance, if I click the generate data button, it's telling me that I'm going to have 2,300 static solutions that I'm going to need to solve. That's a good probably 2-3 hours worth of computation. So one of the things you can do is you can try to increase these increments a little bit and reduce the number of static solutions that you need. So now we're down to 600 solutions. So obviously the larger the increment, the less accurate your data is going to be, but the less time it's going to take to solve it. So inside of here, you have a number of once you hit the OK button, right? A number of static solutions are going to be created, generated, and this is basically telling you where all of your files and folders are going to be saved. So this run form is the same as the optimize run form. It basically creates a series of FEMM models, each one of them stored in here. It creates a series of scripts in order to run those models. Each one is stored in here. creates a series of results all stored in here. And in this case, our transient solution file, which has all of our data for our transient solutions, is going to be installed, or is going to be stored here. Just a quick correction. The results when you click the Generate Data button and then click OK is not stored in the transient solution file, but instead the combined results file. And so now all we need to do is tell it, if you want to change where you're going to store that file, you need to change it here. And you also need to tell it how many FEMM processes can you run at once. So each FEMM process is going to run a static solution. It's going to be completely independent of the other ones. So you are free to run as many as you want. And the point here is that you want to maximize the utility of your CPUs. So if you have 4 cores, you want to run at least 4 FEMM processes at once, right? To completely maximize your CPU. So I usually run around 10 processes at once. That gives me what I think to be pretty close to the best performance for this particular machine, but that again would vary depending upon your hardware. But 10's probably a good number for most people. So obviously I'm not going to run these because it's going to take too long. So I'm just going to load in data that I've already created here. A quick note here, what I've actually done is I've loaded up the neural networks that I've created beforehand. I'll discuss what neural networks are here in just a second. But if you haven't actually created the neural networks yet, click the Load Data button and then find the combined results file that was generated when you click the Generate Data button, instead of clicking on the Load Net button. So once you generate your data, what you're going to end up with are these two entries here in this table. So one of them is for your flux graph and the other one's for your torque. So if I go here to the plot button, now unfortunately the way this plots works is it uses MATLAB. So if you don't have MATLAB, you're not going to be able to create these plots. In fact, you're going to get an error if you try to create these plots. But here's the plot that I just created for this flux linkage graph that we have. You can see I ran my current from 0 to 100, and my rotor angles from about 37.5 up to 60, and you can look at this nice surface that it's created. Now the problem here is that in order to create our transient solution, we have to know what the flux linkage value is for any angle and any current, not just these nice interval points that we created. So there's a number of possibilities that you can try to guess those points by taking the average of the surrounding points. But what I actually did was create a neural network that fits this plot. So if you're not familiar with the neural network, with neural networks, there's some basic information in the under help. You go to documentation. If you look at the user manual, there'll be some basic information in there under what neural networks are and how they work. But basically, a neural network creates a function to where I can just pass in the rotor angle and the current, and it's going to give me a value, and it trains this neural network to give you the best possible fit well, not the best possible fit, but to try to give you a good fit for the data, the original data. So here is the original data, and here is my neural network fit for it. Now the benefit of using this neural network is the hopes that you don't need as much data to begin with, that you can use larger increment values for here, and that the neural network will fill in the gaps for you. That's the hope. So one thing to look at when you're creating these neural networks are this error value here. Again, so here's all the parameters that it takes to create this neural network. There's a lot to it here. I'm not going to go over it now. Again, there's going to be some more information in the user manual. For the most part, you won't have to do anything with this form here. Just note that you have an error value here, and the smaller the error value, the better the fit. So in order to maybe try to get this error value down, you can click this retrain button. So you click the retrain, and it retrains your neural network. It takes a second, and you can see the error value actually went up a little bit. So okay, so now I've actually made it a little bit worse, but it's still probably pretty good. So you did the same thing for your flux and your torque curves. So there's all sorts of things you can do here. You can save the individual neural networks. So if you get a really, really good fit and you like it, then click this save, and then you can save it as a .NET file. That's just a neural network file. You can export the data, or you can view a log. This is a training log. This is the different error values that it had for as it was training. Obviously, there's a lot of data here, but if you're interested in neural networks, this is fun to play around with. Anyway. If you're not interested in neural networks, I wouldn't worry too much about it. I'd keep it pretty much exactly the way it is, and I would look at the plots to make sure they're similar, and just keep retraining it until it gives you a good fit. It shouldn't take that long to do. It shouldn't take that many tries. So once you have these two surfaces set up, now you're ready to do a transient solution. So if you come over here to the Run tab, what we have up here are a bunch of parameters that are needed in order to create or needed in order to solve our transient solution equations. And again, I'm not going to go over the actual equations here, but there'll be more information in the user manual. So please consult that if you want to look at the actual equations. So the first thing you can do is just go ahead and hit the start button. Once you have your neural networks, go ahead and hit the start button, and you can see that the motor is starting to move. All right, and I'll just kind of speed it up here for a second. So you can see the motor starting to move, and what's really cool is that at any point you can click pause, and you can look at your state information. You can look at what the time is, what the angle, the speed, torque, your total electric torque, and the total bus voltage. Or you can look at the individual phases. You can look, say, at phase A. Right now I have 10 volts applied to phase A with 19 amps, about 5 Newton meters worth of torque. You can look at your d phi di or d phi d theta. You can do this for any one of your 3 phases. So one thing you want to know is, how does the voltage actually update with respect to your rotor position? So at every time step, it queries your rotor position to figure out what your voltage is on each phase. And the way it does it by default is basically, if your phase is green, you have your max voltage. So whatever voltage is set up here, you're going to apply that voltage to that phase if it's green. If it's not green, if it's white, then you have a 0 voltage. So in this case, the only phase that's going to have any voltage is A. So you see C has a voltage of 0, you go to A, that has a voltage of 10, which matches this. So if I were to change this voltage up here to 15, and the great thing about this form is it's completely live. So anytime I change one of these values, it automatically updates. So now you can see that my voltage now for phase A is 15, whereas if I go to B, it's at 0. So that's by default that it does that. This is something that you can actually change, and I'll be discussing how you can change that in the next video with regards to these scripts right here. So if you want to know how you change these default actions, go ahead and watch the next video about the Lua scripting. So if I click unpause, and I can end the solution or end the run at any time, restart. So one thing to notice, this video speed, I can make it in slow motion or I can speed it up. What's actually going on is that this is actually slowing down computation. It's not affecting the speed of your motor. The speed of your motor is completely defined by the equations. This is just slowing or speeding up the computation to sort of make it slow-mo or a little bit quicker. So again, all of these parameters are involved in solving your equations for the transient solution. So one cool thing, if you wanted to, so right now there's a 0 load torque, and say I apply a 4 Newton meters of load torque, and you can just watch how it affects your motor, how it starts to slow it down. And I'll change it right back to 0, and you can see the motor now start to speed up again. So it's pretty fun to sit here and play with these different parameters and see how it actually affects the motor as you're running. And there are 2 modes that this transient solution can run in. You can either fix your load torque or you can fix your speed. So right now I have my load torque fixed, so my speed varies. As you can see right now, my speed is actually right about 1500 RPMs. If I fix my speed, I can set it to whatever, let's say 500 RPMs. So now my speed is going to be fixed at 500 RPMs, and my load torque is what varies in order to maintain that 500 RPMs. Alright, so one of the things to note down here is a output file. Right. So obviously you don't just want to sit here and play with this form, you actually want to record data, make some nice graphs, do something like that. So one of the things you have to be careful of, or be conscious of, is this output file. This is where you're going to store data if you start to record data. So if I click the start button and you click record, it's going to start recording data into that file that you had. Okay, so if I click end, give it a second. Okay, so this form is all about creating nice plots, stuff like that. So we're actually going to get into that probably not this video, but a following video. So let's just go look at what this data file created. Oops. Let me find it here real quick. Okay, So here is the data file that it created. It's just a .csv, so it should open right up into Excel. See if you can see this. All right. So here's the data that it collected while I was hit that record button. So as you can see, it records your time, your speed, voltage, load torque, and then for each of your phases, it looks at current, voltage, your torque, your dphi, di, dphi, d theta. Those all for all three of your phases. And it's also going to look at your electrical torque, your power in, your power out, your efficiency, stuff like that. This is all created. This is what by default gets printed out. Now, again, these are what actually gets recorded is up to you, and it can change. And you change that by changing this script here. This is your output script. So this tells basically when you hit this record button, it's going to run this script at every time step. So you can actually change the script and have it output different things if you want to. And again, I would consult the next video on the Lua scripting or this FEMM user manual to get some more information on that. Okay. Right, so I think that will conclude our video today. Again, if you want some more information on transient solutions, please look at the next video. There'll be some helpful hints on how to create these scripts here to really utilize the functionality of Quick Machine. So again, thank you all for watching. Thank you all for using Quick Machine, and have a good day.